Good morning, I'm Dr. Adam Hardy, and today I'm going to be talking about the coheating test, what it is, how we do it, and where it may sit in the future landscape of building performance evaluation. So the principal aim of the coheating test is to derive a value for the heat transfer coefficient, or HTC, of a property. And the HTC describes how much power you have to put into a property to elevate its temperature 1 degree above the external environment. In order to calculate the HTC then, the coheating test tries to do just that. We put in a lot of energy into a property to raise up its temperature. That energy will then be lost to the external environment. So we measure how much power is required to keep it at the elevated temperature, and then we will plot that data on a graph. So we'll plot it on a power delta T graph. If you do this for several days, averaging your temperature data every day and summing your power data, and then ideally you could draw a straight line through those points. The gradient of that line will have units of watts per Kelvin, and therefore the gradient of the line is the value of HTC that you are after, in this case 100. In this picture you can see a simple setup for one of our coheating test experiments. So we want to get that elevated temperature. We tend to do that with electric heaters, although it is possible to use a household's own heating system, in which case we call it an integrated coheating test. We also need to monitor the temperature that's occurring within a room. We do that with a tripod in the middle of the room and at an elevated height, as we want a representative as possible temperature for that room. And then importantly, we also put fans in the property. This is because we want to keep the environment in the coheating test as simple and uniform as possible. We want to avoid stratification. We want a uniform temperature throughout the whole house if we can. And for the same reason, in the coheating test, we will tend to seal up any purpose-built ventilation like extractor fans or trickle vents. This is because if you leave them open, you can have wind blow through your property, reducing your temperatures and making your system go slightly chaotic, which makes the analysis much more challenging. So if we did this test, we did it for a number of days, we would have some data capable of calculating our HTC, but there's some considerations to take into account when you're looking at that data. The first consideration is that you will have undergone some mass charging. So as you switch your coheating test on, your building is going to be very cold, and the fabric of that building is going to be absorbing a lot of your heat energy, and you're not going to be getting up to temperature. So in this case, you can see that for the first 2 days, the temperature was just slowly going up and up and up. And this appears in the power data as well. So for the first 2 days, you have elevated power use, and then it settles down. Now we can't include this first 2 days of data, as this heat isn't being lost directly, at least, to the external environment. It's just going to heat up the fabric. So these 2 days have to be excluded. But there's no set rule as to how long your building takes to charge up. In fact, if we've had big, solid floored properties in the past that have taken weeks to charge up. So you have to keep an eye on this, if possible measure how your fabric is charging with heat flux plates and remove the data for this period before analysis. The second consideration to take into account is solar gains. So unless you're lucky enough to be doing your coheating test in Iceland in the winter, you're going to have some sun. And it may not feel like it, but that sun will be heating up your property at least a bit. That's not ideal for the coheating test because we're trying to control everything and measure all the power that's going into the property. So we have to account for this solar. We do this by measuring how sunny every day is, and then coming up with some estimate for the solar aperture of the building, which describes how that building is responding to that solar flux that it's experiencing. We then multiplied the solar aperture by the amount of solar flux that was experienced that day, and that gives us the power that the building absorbed. And we would then adjust those power numbers and elevate them a bit to account for that extra solar power that was received by the property. But another consideration that you have to think about is any party walls in your property. So if I'm coheating the property on the left, but I don't have any control over the property on the right, there's a pretty good chance that a lot of my heat energy is being lost to the neighbours. And you may very well want to account for this. That's because if you don't control the neighbouring dwelling, then the neighbours could be doing very different things on different days. And particularly if you were doing a coheating test before and after an insulation product, you would want to have as fair a comparison as possible for the system before and after. If the neighbours were heating their property a lot in the before stage but not at all in the after stage, then that wouldn't be a fair comparison. So we really would want to remove the party wall heat loss in that case. We would do this by putting heat flux plates on the party wall, ideally one in every single room that has a party wall, and we can use that to estimate the heat that was lost through the party wall throughout the test duration. And then although we've just added power for the solar, we then end up taking some back for the party wall heat loss, because that was not power, that was not energy that was actually lost to the external environment. The next consideration to think about is that you do have to run your coheating test for a sufficient number of days. So far I've showed you coheating plots like this where the points lie perfectly on a straight line, but of course this will never be the case. You will have some variability on the points, in part due to the imperfect solar correction and party wall corrections that get applied, but also due to other variability. So wind can cause variability, and rain, etc. There's many things that can cause the points to lie away from the true HTC line. And of course, if you were to just do the coheating test for 1 or 2 days, there's a pretty good chance that you will not be able to draw this line perfectly. From our experience, 14 days would be the minimum to get an accurate coheating result, but the more data the better. And also, if you get more data, you're more likely to have a variety of delta t's, which helps to plot that line with great accuracy. If you do end up using less than 14 days of data, essentially what you get is you can still get HTCs, but the uncertainties on those values just end up going up and up and up to the extent that they can become somewhat useless. So in the last minute and a half, I would like to talk about where the coheating method may sit in the future of building performance evaluation. And to do that, I've got a couple of graphs like this, where we have the HTC before insulation product and after. The red bars are error bars, and we tend to say that if error bars don't overlap, then we have a significant difference. Now, if you are putting an insulation product into one property and you wanted to test what the difference was, there's a good chance that the coheating test is the best way to go. Because it is amongst the more accurate ways of methods of getting a HTC. And there's also other building forensics you can do alongside a coheating test that could help you see what was happening with your product and how it was installed, etc. So you can do detailed studies of properties and or products. But it is time and resource intensive, so you can't do the coheating test on a huge number of properties. It's just not possible. And there are other techniques out there that are better in those scenarios. So for example, the Cube or Isabel tests. Now these are promising alternatives to the coheating test. They have been shown to work certainly in some scenarios, and there's validation work ongoing to test other scenarios in which they could perhaps be used. However, they do tend to have a lower accuracy than the coheating test. So if you were looking at the before and after of a product that was expected to have a small impact on HCC, maybe better with coheating, but if it was expected to have a large impact, then you could possibly use Cube or Isabelle. And the real benefit of these techniques is, of course, that they only take a day or two, which means you can assess a much larger sample than you could with coheating. This actually means that the low accuracy could potentially be overcome in some applications, because if you have your before stage and you have several measurements after, although those individual points may have error bars that overlap with the before stage, you can look at the after stages as an ensemble, and you can use statistics to potentially show that the after stages as a group are statistically lower than your before stage. And then finally you have techniques such as the Loughborough in-use heat balance and Smeater techniques. Once again, these are capable of assessing a large number of properties, but they also again tend to have low accuracy. If you can deploy them on a huge number of properties, this low accuracy may not be a problem at all, because once again you can look at your after stages as an ensemble and see how they compare to your before stages. And that is everything I wanted to talk about. Thank you.